numbers. So let's get right to it. The last video, we sort of explored domain a little bit. I gave you a definition for it. We looked at what we can have for inputs that give us a real numbered output. Now, right now, when we say that, a real numbered output, we can have functions that have outputs that are imaginary numbers or complex numbers, defined over the complex. But for things that we normally graph, we're going to restrict this to functions that are defined over real numbers. And that gives us a pretty clear definition of what domain means. So let's check it out. What the domain is for us is the set of inputs of a function, so these numbers that I can plug in, that give us a real number output, something that's not imaginary, and something that is defined, so not the function divided by 0, and that the function can handle. And that's later in the class when we talk about some functions that can't handle like negative numbers. So we're going to discuss that today. We're going to look for the two main problem areas that we're going to focus on, and then there's a third one that we get down the road. So when we talk about domain, you got to keep that in your head. So the set of inputs that give us a defined real number output for a function. There's two problem areas that we really look at. Now, down the road, when we start talking about logarithms, and we're not quite there yet, we'll get there in a little while, logarithms are going to add one more sort of problem area that we have to consider. It's not really a problem, it's just something that we have to consider that, hey, there's some numbers that I am not able to plug into logarithms. There's also some numbers that I can't plug into square roots, or in general, even roots or denominators. So when we think about square roots and denominators, something in our head's got to be like, yeah, we might have some issues with these things. So let's explore those today. We'll look at a few examples on how to find domain, what to be thinking about, and what not to get confused on. So again, one more time, we got this thing called domain. It's a set of inputs that give us a real number output for a function. And for now, there's two areas that we will look for. Later on, we'll add logarithms to this, but for right now, we're going to really be concerned about square roots, and we're going to be concerned about denominators of fractions. So in square roots, if you remember this, when you have a square root, it can be 0. That's what we explored in the last video when we evaluated and said, hey, can you plug in some number that gives you 0 inside of a square root? Yes, that's fine. Can you plug in some number that creates the inside negative? The answer is no. So when we see a square root, in our head we think the inside has to be positive. It's a really optimistic function. It's all got to be positive. What that means is if we plug in numbers that make the inside, the radicand of our square root, that make that negative, those are problem numbers. So what I always like to tell students is that a square root is going to tell you what it wants to have. So it's going to give you this range of numbers, this interval of numbers, this domain of what numbers it wants to have. A denominator, when we think about that, a denominator just says what it can't have. It can't have numbers that make the denominator equal to 0. So when we're filling this out, square roots, the inside must be positive. It's telling you what numbers it wants to have. It says, give me these numbers so I can maintain my positive inside.
On my way.
Denominators, well, they're not about positive. We can have fractions that are positive or negative or 0 on the numerator. There's only one thing that we worry about with fractions. It's that the denominator cannot be equal to 0. And if we keep that in mind, we'll have a much better shot of finding domain. Right now, I just need to warn you, students get these things confused a lot because they they see it a couple times, but they never really understand why it is that you need these cases met, and therefore they confuse us. And they see square roots and they go, oh man, I gotta set that equal to 0 and then solve it. No, that's not what we're talking about. Or they'll see a denominator and say, oh, I need that positive. Why? That doesn't make sense. So let's understand really what is going on here. When you have a square root, if you end up with a negative inside of that square root, that's going to be an imaginary number. And since we're talking about functions over real numbers, that's a problem for us. So how do we avoid real numbers? Is it by making it equal to 0? Well, no. How we avoid imaginary numbers and complex numbers so how we avoid that and stick with real numbers is that we find numbers that when we plug it into the square root, it keeps the inside of the square root 0 or more. In other words, positive and 0. So what we're going to do is we're going to take a look at our square root and say, okay, that's a function.
Let's do it.
I'm looking for the inputs that give us a
Building clear.
real number output. I'm going to say, I couldn't give a
Going
rip if this
there.
thing equals 0. That's fine. Having a square root equals 0 is okay. So if we plugged in,
No more to
let's see,
find.
like 5/4, and we'd have 5 minus 4 times 5/4 would be 5 minus 5 and give you 0, that's totally
Receiving.
fine. But we can also have numbers
Search
that
done.
make it positive. So we're not looking at the idea that let's set it equal to 0. We're really thinking about what a square root needs to have. What a square root needs to have, it needs any numbers that are going to keep this
Roger.
positive. And so how we find it is really, we take the inside of the square root and we let it be what it
Ready
wants
for
to be.
action.
The
On my
inside
way.
of your square root,
Search
it
done.
wants to be positive. It wants to be greater than 0. Greater than 0 in math is the way that we say positive. We also know that we can have numbers that let it equal 0. So in general, we set the inside of our square root
No more to
greater
find.
than or equal to 0. Please don't ever set this thing equal to 0 and solve it. You're confusing a denominator idea with a square root idea. Now, some teachers might have taught you to do that and say, well, then you got to go back and make it an inequality. It's really bad form because sometimes when we divide by negatives, our inequality has to change, and I've seen a lot of students miss that. So, long story made real short, there's two problem areas. There's square roots and there's denominators for now. Later on, we're going to add logarithms to that list of domain issues we've got to deal with.
On my
So
way.
for square roots, we're trying to tell the domain what it needs to be to keep the inside of the square root positive. To find that, we say, well, what does the inside want to be? The inside wants to be greater than or equal to 0. The inside wants to be positive. Let's find the range or interval of numbers that
Ready
does
for
that.
action.
I mentioned to you in
We're on
the
the
first
move.
couple videos that part of this series is reviewing some concepts that we often forget. One thing we often forget is that when we're solving inequalities, there's one time when you have to reverse the
Ready for action.
inequality. It's not when you add or subtract, it's not when you get a negative, it's when you multiply or divide
Ready for
by,
action.
not even when you multiply or divide, just when you multiply or divide by a negative number. So when we're solving this and we subtract 5 and get a negative 5, that's totally fine. We get a negative 4x greater than or equal to negative 5. There's no
Building
reason
clear.
for us to reverse that inequality. But
Clear.
as soon as we divide by that negative, no matter what we get over here, when we divide by a negative, that action reverses our inequality. So
Search
greater
done.
than or equal to becomes less than or equal to. Notice something real quick. If this had not been a negative, we would not reverse that inequality. Even though we're getting a negative on the right-hand side, that does not matter. So
There's
dividing
nothing left.
by the negative, or multiplying by the negative, which we see
Receive
much more rarely. We don't really see that a lot because of the way that we
Receive it.
structure solving equations. But if we divide by a negative,
Going there.
negative 4 divided by negative 4 is x. Negative 5 divided by negative 4 is positive 5/4. But because we divided by a negative, notice we can have a positive number, we are going to reverse that inequality. And here's
Clear.
what this says to you. If you really think about it, internalize what's going on right now, the square root wants to be positive. The inside wants to be positive or greater than or equal to 0. So we say, let's give it what it wants. Let's let it be greater than or equal to 0.
We're on the move.
Let's solve it. And when we solve it, it says, as long
Clear.
as you meet this condition right here, you're going to have numbers inside your square root that are positive.
We're on the move.
That's what we want. So with a square root, maybe this makes more sense right now. A square root
done.
tells you what it wants to have. A denominator is going to tell us what it can't have. So it's a different logic there. And when we say, hey, the domain is this, there's a few ways to write it. Before we go any
Going
further, I
there,
want to make sure
clear.
that you understand one more thing about this. Notice that there are a lot of negative numbers that satisfy this. So x is less than 5/4. That means like
No more to find.
well, 1.25 and less than that. So 1 would be a valid number here. 0 is fine. You plug in 0, you get square root of 5. That's totally fine. When you plug
No
in
more to find.
1, you get 1. Square root of 1 is 1. When you plug in negative 1, well, 5 minus negative 4 would be 9.
Roger. No more to
Square root
find.
of 9 is 3. So negative numbers are fine to plug in.
Ready
Notice
for
that we
action.
saw last video too, that you can plug in
Reporting.
negatives into a square root. That's okay, as long as the result that you get inside of it is positive or at least 0. So this includes a lot of negative numbers. That's not the point of square roots. You don't say, oh, I plug in positives. Sometimes that doesn't work. Like if we plug in 10, 10's a positive number, but 5 minus 20, well, that's negative 15.
Enough sleep, people.
40. 5
We've
minus
got work
40,
to do.
that's negative 35. Square root of negative 35 is an imaginary number. We can't have that. Square roots tell you what it wants to be, so it wants to be positive. We solve it, and then this right here is the interval of numbers that are going to give you a real number output for that function. So we go, yeah, it wants to be this, solve it down. That's going to give you real numbers, and that's exactly what the domain is for us. The two ways to write this are, you can write it like this, but more appropriate than that, it's set builder notation. It says, I'm going to tell you that the set of numbers that works in my function, or that the inputs will give you a real number output, are
There's nothing
based
left.
on an independent variable x. That vertical line is pronounced such that. So x such that x is less than or equal to 5/4. And this right here gives you a set of numbers that works as inputs. Do you see it? Do you see that it says,
Building clear.
hey, if you replace your x such that x
On
is
my way.
in one of anything in this range of numbers, so less than or equal to 5/4,
Building clear.
it's going to be a positive number. And we know that square roots of positive numbers are a-okay. Those are all real numbers. That's what we're talking about. The other way that we can write
Going
this is
there.
with interval notation. Interval notation is where we use those brackets and the
defined.
parentheses. We say, well, you know what? If I had an interval of numbers with 5/4, it
Search
says
done.
x is less than that 5/4. That's this way. Because it has that
Waiting orders.
equals, I
Clear.
include the number 5/4 with a bracket. And this says any number between negative infinity, that's
No
way over
modifying.
here, to 5/4 will be an input that's going to give me a real number output. We always use parentheses for infinities because you can't actually obtain that number. We always have these in order from left to right, just like a number line is. So we start small number and big number. Even if this is reverse going that way, we'd start 5/4 and end at positive infinity. The equal sign
We're on the move.
determines whether we have a bracket or not. That's got to make sense right now. So inputs, in our domain, we want square roots to be positive. We solve it down, and there's two ways to write that domain. The next one. So that doesn't have any square roots, but it certainly has a denominator. This is the other place that we look. We know that denominators can never have 0 on the bottom of our fractions can never have 0 in the denominator. We can't ever divide by 0 and get a real number out. That's an undefined situation. So
We are
this
out of
really takes care of the
resources.
two problems that we have. Number one, well, we can't deal with imaginaries. Number two, we can't deal with undefined numbers in functions to graph them. Now, that does determine some things about graphs, but there's not going to be a point there that we can get out. And that's what that's really the point, is that what is your output for all of these numbers? Well, there's going to be some numbers where we don't have an output that's a real number, or don't have an output that's even defined. It's going to create a vertical asymptote for us when we get to graphing a little bit later. And I told you I was going to talk about graphing a lot. So when this happens, when your denominator is equal to 0 for some numbers, it's going to create this thing called a vertical asymptote. In logarithms and square roots, it just says you can't even get a number out. It's not that it's undefined, it's not even valid for this function. So that's a different story, and that's why we handle them different. Again, square roots tell you what you want to have. You want numbers that are positive. So do logarithms, actually. With denominators, you go, I just can't have this equal to 0. So when we approach it, we think about it like, well, do I care if the numerator is 0?
complete.
You know what? If the numerator is 0, what that actually means is that's where, if we have any x-intercepts, it's going to
No
appear there.
modifying.
Where your numerator equals 0 is your x-intercepts. Your domain, on the other hand, is really only one problem for fractions if your denominator equals 0. So how we approach it, we look at it and go, you know what? I'm going to have problems. If I set my
Building
denominator
clear.
equal to 0, that's going to be a problem. The one problem
We're
we can
running
even
out of
have
stock.
is if t cubed minus 16t actually ends up being equal to 0. So we're going to set this equal to 0, understanding something about it. That the numbers I get here
We're on the
are
move.
bad numbers. They're numbers that I cannot use. They're numbers that will be outside the domain because they're going to create a 0 on the bottom sort of idea. That's an undefined value for an output. So we
Time to
can't
sleep,
include them,
everyone.
and we'll deal with that in the domain right now.
Tomorrow's another day.
So let's solve it. Remember, we're kind of reviewing what you can do. Whenever you have a power 2, power 3 expression that's equal to some number, so some equation here, you might try to factor it. So factoring says put your polynomial in order, and it is. Our exponents are descending. Factor out a
On my way.
GCF. So think about a number and or a variable that divides all of your terms, like t. T divides both of these terms. How do we factor that out? All right, well, and then you keep going. Factoring's not like a one and done sort of thing. So we factor out the t, no problem. We have this, can you factor t squared minus some number? The answer is always yes. I know that you were taught that you can only factor these if that is a perfect square. That's not true. If this number is a perfect square, it does make it easier, and that you can factor this as t minus 4, the square root of 16, and t plus 4, the square root of 16, and that's true. But if that number is not 16, some people will take this and say, I cannot factor that, and that's not true in this class. So when I teach like an intermediate algebra the class before this, I'll tell them that this is possible. It's just that we probably have not covered square roots at that point. Once you covered square roots, we need to understand that this can represent that t squared minus 5. So if you square the square root of 5, you're going to get 5. Well, then if that's the case,
let's do it.
Then we can factor it. And that's perfectly acceptable in this class. So if you have t squared minus some real number, you're going to factor that. Moving on. So once we got this down, so we looked at this, we said there's no square roots, that's great. So, but I'm not thinking positive. I'm thinking, I know that with fractions, my denominator cannot be 0. So I'm setting it equal to 0, understanding that what I get out of this are numbers that I'm going to exclude. Because those numbers, these 1, 2, 3 values that are going to give us 0 on the denominator, they're bad numbers for our domain in that I will not be able to get a real number output. So using a zero product property that says you've got 3 factors, they're equal to 0. If any one of these factors equals 0, it's going to create a true statement in the equation.
Going there.
So t equals 0, no problem. T is 0, and then if either of these are, I don't even care, 0 times whatever is going to be 0. If t minus 4 equals 0, or in other words, if t equals 4, this factor is 0. I don't care what these are because 0 times any other 2 real numbers is going to give us 0. And lastly, for the same reason, t equals 4.
Hostiles inbound.
These things right here, you see it. If I let these t values be evaluated in that function, then this is going to be some number, either 0 or 20 or negative 20. But for each of those 3 values, my denominator is going to be 0. That is not okay. We can never divide a number by 0. Even 0 over 0 is an undefined value. What that means is that you're going to have a hole in the function. That's going to be 30 years from now. For now, that when we get a 0 over 0 idea, it's factorable and cancelable. You're going to get a hole. So your function's going to go around.
They're coming.
It's going to get a hole, and that's what that number does for you. The other 2 numbers, these numbers, you can't plug in any of them. You can't have a 0. That's a bad number. Denominator 0. Got it. If t equals 4 or negative 4, your numerator is going to be some either positive negative real number, and your denominator is going to be 0. That creates what's called a vertical asymptote. What is a vertical asymptote? A vertical asymptote happens when you have this wall,
Requesting support.
force field, and your function goes up to it and says, oh, I can't cross it, I can't touch it. It's like MC Hammer, man.
Requesting support.
Can't touch this. That's what that vertical asymptote does. It says your function cannot cross that. Why?
We're under attack.
Because at that value, your function is not even defined. There is no point at the value t equals 4, and likewise at the value t equals negative 4. Now, I don't know whether it's going to go to positive infinity or negative infinity, but it's going to go to one of them. That's what these values do. I know that's a lot of stuff in a short amount of time, but there's so much to learn about our domain. Most of the time, we just figure out a process, and we go with it, and we never really get it. And then later on, it really kicks our butt, because you'll get into some other stuff where domain's extremely important. And frankly, it kind of hasn't been until we get to like this level and further. In calculus, domain is incredibly important. What you can and what you can't plug in, because sometimes we get answers, and if we assume the domains are real numbers, we're going to be very, very wrong. So I'm going to give you a little recap to make sure that we're okay. Even though it might seem a little basic right now, it's super important to understand these two issues very, very well. So number one, domain is a set of inputs that for now, because we're talking about real numbers, must give us a real number output. That means square roots, because they have the potential to give us imaginary numbers, are a problem area for us to look at. And denominators, because they have the potential to create an undefined undefined number value, are a problem for us to look at. Notice, cube roots are fine. You can have negatives in cube roots, or fifth roots, or seventh roots, or odd roots. Even roots, like square roots, fourth and sixth roots, those are all going to have that same issue. Those will be problems, and we're going to have domain issues there. Now, there's a difference between square roots and denominators. Square roots, we solve these domains, or we find these domains, by letting this be greater than or equal to 0, because we think about it, a square root needs to be this. It needs to be greater than or equal to 0. Notice the needs to be. It wants to be this. This is the definition of what makes a square root work over real numbers, is set it greater than or equal to 0. It's going to give you an interval of numbers that is going to work for you. That's going to create the inside positive. That's going to give you a real number result output. Denominators are backwards. Denominators aren't given by what you want to have. It's given by what you can't be. So with a denominator, it can't be 0. So we set it equal to 0 and solve it down and say, these things are not okay. If I let those happen, I'm going to get some bad situations for us as far as the domain. Now, graphically, they do help us. So we use this to graph. I already told you that's going to be a hole. Those two are going to be asymptotes. If you have 0 over 0, that's a hole, a little removable discontinuity, something that's just a missing point. These two things are vertical asymptotes, and we're going to learn a lot about it. But as far as domain is concerned, those are problems that we must exclude. Notice, this says what I can have, what I must have to make it work. This says what I must not have to make it work. Do not confuse the two. So for our domain, we can say x, not x. Why is that wrong? Why is x wrong? Remember that this first thing in set builder notation is the independent variable. So if my variable changes, I need to change that and say, look for t's. Okay, what can t be? T can be all real numbers except, or but, or and then we list our exclusions, and we say, you know, we've got to exclude some values because they're going to create some undefined results for us. That's t equals 0, and t equals -4, and t equals +4. Those three numbers are the only numbers in the world. Power 3 says we're going to have at most 3 results. Power 3 says these 3 numbers are the only numbers in the world that are going to create a denominator equals 0 and therefore an undefined result for us in this function. It doesn't matter about positive or negative, it's a fraction. They can be positive or negative. Don't confuse a square root with the denominator idea. How we do this with interval notation it's fairly ugly. You see, when you exclude one number, how we do that in math, how we do that with interval notation, is we say all real numbers would be this. Check it out. All real numbers would be that. That's all real numbers, from negative infinity to positive infinity, no problem. If we want to exclude values from that, then we're going to insert 4 little exclusions. Well, how do we do it? We insert an exclusion by putting this in order and saying, you know what, I can go from negative infinity all the way up to -4, but parentheses exclude values. Brackets include them, parentheses exclude them. So this would be like -4.00000000000 for a long way, and then we'll 1, and then say, yeah, but -4 is not included. And then we'd start up again at -4, but a little bit more than that. So this says, hey, go from negative infinity up to -4, but just before you get there. Now, just after you've left -4, and that's what excludes this point, -4. Then you can go all the way up to 0. Notice it's in order. But you've got to exclude the 0, and then you can go up to 4. But then you've got to exclude the 4, but then you can continue on. Square roots Give you an interval, says what you can't have. Denominators say, here's an interval, and it says what you can't have. It's done two different ways. That's got to make sense before we go on any further. So we need the idea of inputs as domain. We need the idea that it's the set of values that's giving you a real number output. And if you think about that, it really should just follow directly that square roots want to be positive because negatives give you imaginaries. Can't have those. It's got to follow that denominators can't be equal to 0 because if that happens, we get something that's undefined. We're going to come back with just a couple examples. It's going to be pretty quick. Going through and exploring these ideas a little more. Remember that later on we're going to add one more scenario to this for this class, and that's logarithms. Logarithms fall into the same category as square roots in that the inside, the argument, wants to be positive. So if you're dealing with that right now, all we need to do with the inside of a logarithm is set it greater than 0. It can't even equal 0. So logarithms, the inside has to be positive because of the way it comes from an exponential. When I take a number to an exponent, a positive number to an exponent, I always get, we always get positive numbers out of that. And since our basis for exponentials are positive, our output for exponentials has to be positive, and therefore input for logarithms, since their inverses, have to also be positive. So that's the other domain issue. We deal with it much later, and I'll explain it thoroughly when we get there. So I'll come back in a little bit with 2 examples. Okay, so I lied. I said 2. I meant 3 examples, because I really want to deal with that one too. We just talked a long time about what inputs are as far as the domain, and that these inputs need to give you a real number output for your function. And if that doesn't happen, well then you got to exclude them somehow, or tell the domain what it has to have in order to make this function work for you. And we looked at 2 parameters. We looked at square roots and denominators. And I said, there's going to be another one, logarithms. I'm going to kind of hide it for now. We'll talk about it later when we get to logarithms. And
Chief,
really,
this
really
is the same transmission we received before,
what happens
but
if
the
your function
signal is
doesn't have square
incoherent.
roots,
Our
and it doesn't
walkie-talkies
have
are not
denominators,
powerful
and
enough
it
for
doesn't have
long-range
logarithms?
communication. We
Well,
have to build
then
a
your
large
domain
antenna.
is all real
A local
numbers
library or
for every
university would be a
polynomial
good
that you
place
have.
to search for
Every
information on
polynomial,
how to make
that's
it
things
work.
without square roots. That's things without fractional exponents that are radicals, like square roots. That's things without fractions where you have a variable on the denominator. Notice I don't mean fractions like this.
Let's go there.
Fractional coefficients like 3/5, that is not what we're talking about. We're talking about fractions where you have variables on the denominator.
Receiving.
You don't have
Receiving.
square roots, you don't have fractions on the denominator, where variables on the denominator, you don't have logarithms. Your domain is going to be any real number, all real numbers. So if you look at this and you go, hey, no fractions at all, no square roots, no logarithms, your domain's all real numbers.
Roger.
So how do we write that?
Ready for action.
We can say x such that x is a real number, or x such that x is all real numbers, or x such that x
Building
is...
clear.
You can use a block letter R for all real numbers. Or we can say, in notation,
Going there.
negative infinity to positive infinity. That's another way that we can say all real numbers. And what that says is plug in anything, you're going to get a real number out, and that's true for that function. If we move on to something like this, though, man, that's nasty. There's a lot of stuff going on there. Don't be confused when you see both fractions and square roots. What we deal with here is each of those
Operator,
issues independently.
let's do
So
it.
you don't have to put them all together. We're
Clear.
going to on that one. I'll show you. It's a nice little trick we can use. But you don't have to do that.
Ready
We
for
can
action.
think, okay, well, I have a denominator and I have a square root. Let's think through both of those. So let's do the denominator first.
Waiting
What do
orders.
you know about denominators? Well, we know that denominators equaling 0 is a bad
Receiving.
thing for us. I could put in any number here for the denominator, as far as the denominator is
Going there.
concerned, as long as it does not equal 0. So when we do this, when we see a denominator, it's telling you there's numbers that I can't be, okay? So there's numbers that I'm plugging in here that might be issues. So we're going to set this equal to 0 with the understanding that it's a denominator. If it equals 0, I'm going to have problems. So when you
There's
add
nothing
4 and
left.
say, hey, that number 4 obviously is going to create a 0 on the denominator. I don't even care what's on the numerator
Clear.
right now. If this function, we allow, if we
Building
allow
clear.
this function to have x equals 4 as an input, we're going to have an issue right here. That's a problem issue, so we say we must
Let's do
exclude 4 So setting the denominator equal to 0, not greater than
Clear.
or equal to 0, says you're going to have some bad numbers here, or numbers that you can't have in your domain.
Clear.
And that one of those numbers is 4. Now we look at our square root, and we understand that something's switching. We're not worried about 0 so much, we're worried about keeping it positive, because we need real numbers. Yeah, real
We're on the
defined
move.
numbers. This would
We are
create
out
an
of
undefined
resources.
number. Let's think about here. I need values of x that keep this part of my square root greater than or equal to 0, to keep it positive or 0. Well, what's that going to be?
Building
Solve
clear.
it, it's going to give us a range of numbers, some interval that's going to keep the inside of my square root positive, and that's what I need to have happen to get a real number out of that square root. So if we add 15,
Wrap it up, folks. Time to call it a day.
On my way.
we do not switch to inequality ever when we're adding or subtracting. And divide by
Reporting.
2,
On my way.
we do not switch to inequality unless we divide
Ready
by
for
a
action.
negative.
Operator.
This says that as long as you have numbers greater than or equal to 5, you're going to keep the inside positive. As long as you keep the inside positive, you're going to get real numbers out of that square root, and that's what we need. Do you see the difference between how we treat denominators and how we treat square roots? You've got to see the difference. One is about keeping it positive so that you get a real number. The other one, the denominator, is about not letting it equal 0 so you don't get something undefined.
Let's do
And
it.
understanding that
There's nothing
we
left.
need real numbers out that are defined is how we approach dealing with square roots and
We're on the move.
fractions.
Operator.
Now,
Operator.
we will put this in the domain and say, all right, set builder notation x such
Let's
that,
do it.
and we're going to put both these up there, right? X needs to be greater than or equal to 5, and x
Ready for
cannot
action.
equal 4, and then we're done. And your teacher's probably going to go,
We're on the
think
move.
about this for a second. And not that you're wrong, all right? Not that you're wrong, but that it's redundant. Look at how this says x needs to be greater than 5, and look at how that says x
Going
can't
there.
be 4.
Operator. Take him
All
down.
right. So
Waiting
we
orders.
know,
Back
right?
up.
We know that this has to happen. We have to have that in order
Requesting
for this to
support.
get real numbers. But then it goes, oh yes, but make sure you don't get a 4 in there. Isn't this already excluding 4? So our x says, you gotta be more than 5. And then it's, yeah, make sure you don't get a 4. Well, that's a redundant thing. So we really would not have this
Clear.
x is not equal to 4 for this scenario. We don't need it.
On
That's
my way.
redundant. Now, I'm gonna play around with it a little bit.
Ready for action. Building clear.
What would happen? What would happen if, you know what, I'll do this too. Our interval notation would be, here's 5,
Clear.
here's greater than that. So we'd go from 5 to infinity, parentheses on the infinity, a bracket on the 5, because we can actually equal that value. So this would be our two domains for this scenario.
Operator. On my way.
Let's play around. What if I made this
Waiting orders.
not 15,
Clear.
but 12? Well, that's not fair.
Search done. On my way. Let's do it.
If we end with, hey, in order to make that square root positive, you
Search
need
done.
numbers bigger than or equal to 4. All right, I need
Reporting.
numbers bigger than or equal to 4. Is this now relevant? Absolutely. Because this says I need numbers that are greater than or equal to 4.
Clear.
And this one says you
There's nothing
can't
left.
equal 4. Now, instead of writing this, it's a little bit easier to write these together. If we say that x has to be greater than or equal to 4, and this one says x can't be 4, then this is one way to say it, but maybe more importantly, or more appropriately, we can say, what if we just exclude that equal sign? That says that x has to be greater than or equal to 4, but not equal to 4. It just takes out that equals part of it. And so what we get
Going
here
there.
is this domain, so x must be more than 4.
Clear.
Or, using a parentheses, x must be more than 4 can be written in interval notation just like that. Okay, last iteration of this. Let's change this to 9.
Ready for action. Going there. Let's do it. Reporting.
9.
Roger.
9, 3, 3,
Roger.
3. What now? Is
Waiting
this
orders.
relevant? Yeah, absolutely. This says
Reporting.
you need numbers that are greater than or equal to 3 to keep this thing happy.
Going
And
there.
since 4 is now in that interval, you need to express it separately and say, I also can't have 4. That makes sense. So, hey, you know what? You need numbers more than 3.
We need a workspace where we can experiment and re-engineer all the pre-pandemic technology. We could store all the books there, too. Let's build a research center and assign the most technical minds there.
We would say we do this. Because 4's up here, right? 4 is this problem. So we'd start at 3 with a bracket. You can include the 3, and you need to. We'd go up to 4. We'd say, you know what, you need to exclude that 4, but then after that, you can keep going forever. That's how we write that interval notation.
Let's
Man,
do
I hope
this.
this makes sense. I hope you're seeing the ideas behind domain
Operator.
really producing
Search
fruit.
done.
Understanding real numbers here being positive.
On my way.
Define numbers here being not
Chief,
0. And
we've
that
just
is
got a
how we
shitload
approach
of supplies.
finding a domain.
Some
The
prepper
last
must
one,
have
we'll
lived
go
here.
through it very
They
quickly.
piled up
Obviously,
enough
we
to
have
survive the
fraction.
apocalypse.
We also
God
have some
bless
square
these
root.
preppers.
So let's really think about it. There's 2 issues,
That's
right?
great news.
We know
Take
that
it
the
all.
denominator has a square root in it. We know that square roots want to be positive. So when we write this, you go, let's talk about
Ready
the
for
square
action.
root first. Let's understand that in order for us to get real numbers, I would have to have x minus 8 being greater than or equal to 0. That's the square root idea. Just the square root idea says keep me positive or at least 0. So I want this to happen so that this guy's happy and gives me non-imaginary numbers, gives me real numbers. But it's on the denominator. Denominators say, I get that you want to be greater than or equal to 0 because you're square root, I get that, but remember, denominators are not happy if they equal 0. So what if we just don't include the 0 part of it? Now we've excluded the only value that can possibly make that 0, and it would be 8. So 8 minus 8 is 0, the square root of 0 is 0. So if we exclude the 8, if we exclude that idea that hey, I can be equal to 0
No
here,
more to
then we're
find.
excluding the only number that's going to let that denominator be 0. So we kind of put these ideas together sometimes and say, cool, but we know what, we can't have that actually equal 0. So we're just going to take that away from that inequality. If we add 8, nothing changes as far as reversing inequality. We get x is greater than 8. That's our domain. We can set this up with set builder notation. We can say, hey, x is positive
On my way.
and more than 8, but it can't include the 8. So our interval notation says, let's start at 8 with a parentheses. We cannot include it because that would make 0 on the denominator fraction, and we go to infinity. I hope that this has made sense. There's only one more thing that I want to touch on. Sometimes you'll get some fractions like, let's say 5 over x squared plus 1. And you go, all right,
Building repurposed.
great. Can that denominator, let's think through it. Does it have any of the problem areas that we know
There's nothing
cause
left.
issues for us? Well, it doesn't have any square roots. It does have a denominator. And so you go through the process and go, you know what, I know that if denominators equal 0, I've got problems.
No more to find.
But then you think about it and go, can that actually equal 0? And the answer is no. Not over real numbers, and that's what we're talking about. So if I take any number in the world that's a real number,
Search done.
and I square it, which gives me a positive, or at least 0, and then I add 1 to it, there's no way it's going to equal 0. That's
There's
impossible.
nothing left.
Positive numbers plus 1 can't equal 0. And so this says there's no solution to that, no real number solution. That's fine. What that means is that there's no real solution that's going to
Adaptation
make your
done.
denominator equal 0, then there's no problem. There's no domain problem here. Your domain would be all real numbers
No more
for
to
that.
find.
Even here,
Receiving.
if I take a square root of that and go, oh man, I know square roots have to be positive. So you think about this one and say, all right, the square root of
On
x
my way.
squared plus 1 has to be greater than 0. Not equal to 0 because it's on the bottom of a fraction. You go, well, what numbers are going to make this greater than
Search
I
done.
can't even solve that. Oh, geez, what do I do?
Reporting.
Well, if you square a number and add 1, is it always
Waiting
positive?
orders.
Is it ever negative? It's never negative. It always has to be positive or real numbers. That's also telling you the domains are real numbers. So sometimes you really just have to sit there and think about it a little bit and understand the ideas
Going
behind
there.
the square root and the denominator. If you have something that cannot equal 0 on the bottom of your fraction, your domain's all real numbers. If you have something in a square root that cannot be negative ever, no matter what you plug in, then your domain is all real numbers. So I hope that you'll get this from time to time. I hope that makes sense to you. I hope also you understood my comment about with fractions, we're really only concerned where your denominator has variables in it. So like x minus 2 over 4, that 4 is a constant. It can never equal 0 on its own. So your domain here would also be all real numbers. We're going to stop there. We've explained what domain is again. We've talked about how to find it with square roots and with denominators and the interplay between those. Later on we'll talk about logarithms. I hope it makes sense. And we're going to come back in a little while with how to find operations of functions and their domains. So I'll see you for the next video on it.
Stop working. Start winding down for some rest.
Let's do it.
Welcome to another video. Today we're going to explore operations of functions. And when we talk about operations of functions, I really want to focus on what happens with the domain. Most people can understand that you can add two functions, subtract two functions, multiply two functions, and divide two functions. It's not that hard. But what happens with the domain is important. You see, sometimes in math, it looks like you can cancel out a domain problem. You can never, ever do that. So when we talk about domain, we're going to jump right into it here. When we talk about domain, it's one of the most pessimistic attitudes that we have, right? So domain is like the skeletons in the closet. You can't ever get rid of them. They're always there. Like it carries its baggage with it all the time. So when we start to compose functions or add functions, subtract functions, multiply, divide functions, even if it looks like the domain of your resultant function is getting better, it's not. What that means is that if we give two functions, the first thing we do is find the domain for each of them. This is very easy because I gave you a nice one that's the same. And then if we add them, subtract them, multiply them, or divide them, we are going to have both of those domain issues in every one of these cases. And then, what's even a little bit worse about it is that we can even develop some new domain problems by doing these operations. So that's what we're going to be looking for in this video. I'm going to show you how we can add, subtract, multiply, divide functions. We'll simplify them as much as we possibly can, and then we'll discuss the domain. So let's start right now. Whenever you're going to do operations with functions, whether that's going to be addition, subtraction, multiplication, division, or if you're going to start composing functions, the first step that we do is we find the domain for each of our functions individually.
On my way.
Now here, they both got fractions, and after watching the last video, you know about fractions. You know that we're looking for inputs that give us a real number defined output, which means for fractions, denominators equaling 0 are bad things. We're going to set our denominator equal to 0.
We're on the move. Reporting.
Understanding that when x equals positive 2/3, that's a problem for us. And it's the same problem for both of these fractions. I gave you the fractions like this with the same denominator so that we can add them and subtract them easily. I'm not trying to teach you that. I'm trying to teach you what happens with the domain here, especially with this case. So here our domain says you're good as long as x cannot equal 2/3. And sometimes we even abbreviate that and say, hey, x such that x does not equal 2/3. X such that x does not equal 2/3, implying that all real numbers work except for 2/3 because that would make my denominator equal to 0, and that creates an undefined result for that particular input. So that's got to make sense. 2/3 as an input don't work because your output's undefined. Now, when we start adding functions together, I need you to remember, I need you to know that no matter what we get, this right here is going to be the domain, at least. This right here is going to be in the domain of our resultant function. We could get worse things from it, but we can't ever get rid of these problems. They stick with your functions forever, no matter what you get. Now, typically with addition, subtraction, and multiplication, you're going to see the same domain problems come up again at the end, so it's not such a big deal for those, but for this one it is, and we'll see why in a minute. So, f plus g of x. If we add these functions together...
done. There are some infected around here. Going there. Waiting orders.
Keep in mind that we need a common denominator to add fractions, and we have that. So we're just combining the numerators right now. That looks like 6x plus
Operator.
3.
They're trying to get inside.
Over 3x minus 2. Yeah, you can factor the numerator, but it's not going to help you simplify, so I would leave it just like that. Because if we ever have to deal with it later, the first thing we're going to do is probably distribute that numerator.
Waiting orders.
Denominators should always be factored. So if not, you should factor
You're
that.
out
Now
of
here,
resources.
you can't do it, but that's something to think about. And notice something. Your resultant function here has the same exact denominator, obviously, as what we started with. That means that your domain's going to be the same. Even if these denominators had been different, you would have found a common denominator, wouldn't you have? Which means you'd have the same factors. And those factors equaling 0 would cause domain issues for you.
Reporting.
So even if your denominators are different, you'd find a common
We're on the
denominator, and these things would appear again, whatever they are, in that result. So our domain says, hey, I'm going to be exactly like how you started. The same thing's going to I'm going to be exactly the same domain as what you started with for both of your functions combined, whatever those are. Here they were the same. They don't have to be. They just be different denominators. F minus g of x is identical, except that we're subtracting. But we're also going to see that when we subtract that 4x over 3x minus 2, I have a 2x
Sir,
minus
the
a
people
4.
have reported hearing a lot of noises coming from underground. They're afraid that it could be infected moving through the sewers and tunnels. We need to bolster our defenses and be ready to attack from within, too.
So minus 2x or negative 2x plus 3 over 3x minus 2. Again, there's no simplification that we do, and we see that the domain that we had originally is going to be the same domain that we get when we subtract functions.
Receiving. On my way.
You know what? If you think about it with multiplication, think about what
On my
happens
way.
when you multiply fractions. Well, you take the denominators and you multiply them together, and they basically become the new denominator for your fraction. Now, if we simplify stuff, we can accidentally start simplifying away one of those domain problems. But if you think about what happens in the domain,
On my
I'm going
way.
to have one fraction with the problem on the denominator, and another fraction, in general, problem on the denominator. I'm going to multiply them. That becomes my new denominator. Do you see how I'm just going to keep combining my domain problems for addition, for subtraction, and even for multiplication? We're going to get the same domain here moved over to this. That's going to be the same domain as what our result is what we started with.
Search
so
done.
This 2x plus 3 over 3x minus 2, probably with parentheses would be good here.
Going there.
Multiplying fractions says multiply your numerators, we're going to distribute to 4x. Multiply your denominators, we're not going to distribute at all. Your denominators should always be factored as much as possible. So instead of distributing 3x minus 2 times 3x minus 2, we leave them factored for a variety of reasons. One of them is because when we graph these things, it's really nice and very appropriate to have your denominator factored. It would create a vertical asymptote. We haven't got there yet, but I said that in the last video. It created a vertical asymptote at two-thirds. At x equals 2/3. That's this kind of force field you can't touch. And then because that power's there, because we're going to have this group as 3x minus 2, the second power, it's going to tell us a multiplicity of that. We're going to get to multiplicity later. So we'll distribute numerators, absolutely. So that's going to be 8x squared.
We're on the move.
Plus 12x on the denominator. Leave your
You won't
denominator
believe what just
factors.
happened.
I don't care
One
what
of the
these things are.
infected
They're the
just
same
followed
amount.
us outside.
Leave them as factors. It's
Into
going
the
to
sun.
really help you with
Going
growth.
there.
Promise.
He
And
seemed to
if
know
we have to,
exactly what he was
add
doing.
fractions or
It took him a moment to give up, but then he returned to the dark.
Waiting orders.
What the hell is going on?
Let's do it. If we leave these factors. Now, because we have
Better get
3x
back
minus
there
2
and
times
kill
3x
it.
minus 2, that's a repeated factor. That's repeated multiplication. That's an exponent.
Receiving. Reporting.
That's how I want to see it. And do you
Going
see
there.
that no matter what,
Ready
because
for
we're going to
action.
keep these factored, you're
Roger.
going to see the same exact
Building clear.
denominators that you had here, so the same exact domain issues that you had here,
Let's
those
do
are
it.
going to repeat over here. So our domain doesn't change. Our domain
Building clear.
says, yeah, your domain for this is x's such that x cannot equal, again, 2/3.
There's nothing left.
I want to reiterate this. I know that I haven't taught it to you yet, but you know
On my
how I
way.
teach at this point. You know that what I'm trying to do is prepare your brains. I'm giving you an advanced
We need more
organizer for
resources.
later on as to why you do this. Sometimes if you don't know why you do something, it's really hard to accept that you have to.
This house is
You
infected!
have
Get
to do
inside!
this and leave it factored and write the exponent because later on, this is going to give us a vertical asymptote on a graph at that value. So a vertical line. X equals a number is a vertical line. If x can't equal that vertical line, well then you have something you can't touch, can you? Do you? Can't.
We're on the move.
You have something that you can't touch, don't you? Well, if you have something you can't touch, then you have a vertical
Start
asymptote,
working.
Receiving.
and
Start
that
winding
power
down.
says that you're going to be even. Even functions match up. So we're going to look like this or look like this around the asymptote. That's why we leave it that way. I'm going
Waiting
to flesh
orders.
that out into a few more videos. So, long story,
Operator.
as short as I can make it,
Receiving.
domain is still really relevant for your functions. We talk about it lots and lots moving forward. Find
my
your
way.
domain first. If you have to add, subtract, or multiply functions, you're going to get the same domain. Almost exclusively. There are times when you don't, but almost exclusively you get that. If you divide,
There are some
not only
infected
are you going
around
to get
here.
the same domain, you could add some other issues to that domain, the domain problems you already have. The key here, though, is that when you start dividing, it's going to look like you can cancel out some stuff. It's going to look like your domain doesn't have a problem anymore. You still have the problem. It's just hidden. So I said this at the beginning, and it's going to make some sense as we go through. But these issues, this x you can't
No
equal
more to find.
2/3, that issue, because the resultant function starts here. It is these things just wrapped up together. Because these are those root, if you will, functions, you
No more to
can't
find.
have that 2/3. No matter what we get here, I can promise you that our domain is going to exclude 2/3 from it. It's not going to look that way. It's going to look like we
No more
cancel
to
it out,
find.
but it still has to be there. So when we divide functions, we're really conscious of what goes on the
No
numerator
more
and
to
what goes on the
find.
denominator. It says f divided by g. So f is this
Search done.
2x plus 3 over 3x
Reporting.
minus 2. Divided by, you can even write a divided by sign if you want to. 4x over 3x minus 2.
Reporting.
Now we know something about complex fractions. We know that fraction divided by fraction, when we divide, so fraction divided by fraction, when we divide fractions, we can reciprocate and multiply. So instead of
Operator.
this, we'll reciprocate the second fraction, or the
Waiting
bottom
orders.
fraction in this case.
Ready for action. Receiving.
All right, so I have my first fraction.
Going there.
Division says multiply by the reciprocal of the second fraction. And you go, wait a minute. Oh, this is awesome. Because look, boom. Oh, I can cancel
Ready
out
for action.
my denominator. I can cancel out one of those domain problems. It certainly looks that
Let's
way.
do it.
It certainly looks that way. But because of where this came from, because your original functions had a domain of negative of 2/3 is a bad number, so x cannot equal 2/3. We actually write that down first. We go through this and go, all right, I know x can't equal 2/3, and no matter what
We're on the
happens, x cannot equal 2/3. Even if I start canceling stuff out, I know that where it came from, the baggage it holds onto, the skeleton in the closet, that's if you can't see. is you cannot allow this
No
function
more
to be
defined.
2/3 based on those root functions, those functions we started with.
No more defined.
The other good news here is that
We're on
we
the
can
move.
add
No
some
more defined.
problems to it. So notice our resultant function that we got that 2x plus 3 over 4x. And you think about it, you go, wait a minute.
No more
Wait,
defined.
that's a fraction with a different denominator than I started with. Yeah. And we know that denominators equaling 0 are
No
bad
more defined.
things. So if we continue to go, all right, let's find the domain of this. Say, well, 4x equaling 0 wouldn't be good, because that creates an undefined issue for an output, and we know that the domain needs inputs to give us defined real numbers. And I divide by 4. 0 divided by 4 is 0. You go, okay, yeah, hey, x equaling 0 would be not a great thing here. We'd get 3 over 0, that's undefined, so I know that I'm going to exclude 0. If we ignore this and have that, we do understand domain, but we're forgetting to realize where the functions came from. So when we go ahead and we do division, how to appropriately approach this is find the domain first. When you start dividing, make sure that you write that domain down. You go, okay, whatever these are, you're going to have it here no matter what. And then we might even get additional domain restrictions that we have to add to that. We have to exclude that from the domain. So even though it looks like the 3x minus 2 cancels out, it does, but the domain issue is still there based
The
on
work
what we
ain't
do.
gonna wait for us.
Hope that makes
Let's
sense.
get to
We're
it.
going to go ahead and do one more really quick one just to talk about a square root, to hit that one more time, and then we'll be done. Okay, last one. So we're going to add these, subtract these, multiply these, and divide
Operator.
these functions, and we're focused on the domain. So really, if you want to stop this and go through here, your first process should be, let's think about it, find your
On my
domain
way.
first, and then recognize that no matter
Let's do
what
it.
I do, I'm going to have these two domains in the result of every single one of these function operators, and I might even add some to it. So I'm going to have at least what's here, and maybe add domain problems as we're doing these operations.
Receiving.
So let's go ahead.
Waiting
Let's do our domain. Oh man, so think about it. Last time we're going to think about domain
Reporting.
like this for a while. So I look at the square root and I think square roots are this idea that they want to be positive. So it tells you what it wants to be. It says I
Chief,
want
we found
this
some medical supplies.
inside
They'll definitely come in
this
handy.
Vatican
Now we'll be able to give
be
first aid
positive,
to the
or
wounded.
at least
But if we
zero.
want to
So
heal
when you
people
think
more
about square roots,
efficiently,
you say,
we'll need to
I
build a
need
med
real
bay.
numbers here. What makes it happen? Makes it happen if the inside is greater than or equal to 0. If not, I get imaginary numbers. That's an issue. I subtract 3,
Clear.
and it says that I need x to be greater than or equal to -3 in order for this to give me real numbers out. That is the domain of that function.
Roger.
Then we go to denominators, right here, this function, g of x. So what about denominators? In order for this
Area
input,
scout.
these inputs to give me a real number defined
We're on the
value
move.
out. Well,
Medbay
it's
sounds
not
like a
about
good
negative or
idea.
positive, it's about
We'll think of
defined
that.
values for fractions. We know that if x equals 0,
Building
I'm
complete.
going to have my denominator equal to 0. That's giving me an undefined value. That's going to be a problem. So any positive is fine here, any negatives here, fine here, but we just cannot allow 0 to be an input for that particular function. So we're going to say that, yeah, x cannot equal 0. That needs to make sense before we go any further. So when we look at square roots, we think, what's going to give this,
Clear.
or what inputs will make this function give us real number defined outputs? For square roots, you got to keep them positive, solve it, and these are the numbers that keep it positive and give you real numbers out. For fractions,
Waiting
denominators
orders.
cannot equal 0, because if they do, you get an undefined value.
Building clear.
So square roots positive, denominators can't be 0. These two domains are going to follow us for every single one of these,
No more
and
defined.
we might get some more restrictions out of it. What can't happen,
Adaptation
even if you
complete.
start canceling stuff out, you are still going to have these. So you never ever cancel away domain restrictions. So if you wanted to do this right now, say, hey, what's my domain? Well, I know that
We're on the move. Building clear.
that's going to happen. No matter what I get here, I know that because they never go away. Also, do you realize that this is not irrelevant here? We had a case last video where we didn't have to put this because it was included in that.
There's nothing
Well,
left.
or sorry, it wasn't included in that interval. Since this says x can be any number bigger than -3, and 0 is in that interval, we have to show explicitly that we're excluding it, either this way or with interval
Ready
notation
for
as
action.
showed in the last video. Or we can write it here too, same thing. And that might be a really good option for you.
Roger.
To, before you even do any of this, write down the domain. It's not going to change. The only thing is you might have to add some more to it. That could be the case. Well, let's go through adding, subtracting, multiplying, dividing. The first three are going to go very quickly. So if we add these functions, there's nothing to really
Construction
combine.
ready.
So adding function says, hey, you're just going to have that x plus 3.
Let's
You're
do
going
it.
to add 5 over x, and it's very clear to
Receive it.
see that that's still the same exact domain. Or if you subtract them, same thing. X plus 3
We
minus
finished
5
construction.
over x. Same exact domain. Or multiply them. I'd probably put the 5x first. Because multiplication is commutative, we can do that. 5 over x times
Receiving.
x plus 3. You can even make it one fraction. 5 times
Building
x
work
squared root of
done.
x plus 3 over x. And you see that we have the same exact domain. It's not going to change. Now the division.
We finished construction.
We do have to be conscious of what's coming first because
We are
division
out
is
of
not
resources.
commutative. So we have to put the square root of x plus 3 on our numerator. And we'd have to have 5 over x on the denominator. Well, wait a
On
minute.
my way.
When we're dividing fractions, we multiply by the reciprocal. So this
Building
would
work
be the same
done.
thing as the square root of x plus 3 times x over 5 times the reciprocal of 5 over x. So here's x, you can think about square root of x plus 3 over 1. So square root of
There's
x plus 3
nothing
over 1
left.
Get some rest.
divided by 5 over x, or multiplied by x over 5. You know, this is fantastic. I can simplify this just a little bit. Maybe put my x before that square root.
Clear.
That's the resultant function of dividing f by
Going
g.
there.
We divided square root by a fraction. When you divide fractions, you
No
can
more to
multiply
find.
by the reciprocal. No problem. We would have x times square root of x plus 3, we'd have over 5. This is one of the
No
reasons
more to
why
find.
that might be a really good option for you to do first. Do you see it? Do you see
Search
how
done.
the denominator changed for us? The
Hostiles
denominator said,
inbound.
well, there's no longer an x there. So if you were to just do
Search
this
done. Someone
and
incoming.
then think about the domain, you're probably going to miss that. Don't miss that. This is why the technique
Going
I
there.
works
Search
really
done.
well. Find the domains first. If you want to write them down for every operation, do that. Even for compositions, that sort of works. Really, we take the domain of the
Building clear.
inside function and the final function.
Infected
We
incoming.
combine it that way. But for adding, subtracting, multiplying, dividing, you're always going to get the same domain, no matter what. We started with that.
Operator.
We don't add anything new,
Requesting support.
because look at that, the square root hasn't changed. So that's still
We're
the
under
same
attack.
domain that we had. The x is gone. It looks like
We
that's
need
gone.
backup.
The
They're breaking
requirement
into
for
our
x
building.
equals 0 is gone. But because of where it came from, we have to retain it. But our denominator cannot equal 0 anymore. That right there can't equal 0.
door
So you
won't
don't
hold
gain
much
any
longer.
new values. You still have the same coordinates. I hope that makes sense. Hope you understand at this point that your domain does not change from the original functions when you're doing
Ready
these
for action.
operators. You
Kill
can
them.
only kind of make it worse.
We'll get them.
So practice that. I hope
Kill
that makes
them.
sense. Next time
Let's
we're
do
going to
it.
talk about some graphs of functions,
The door won't
determining
hold much longer.
if one input has to be an output, what that looks like. So we'll do something called the verbal line test. You've probably heard about it, but just for why it makes sense. We'll talk about even versus odd functions.
We're on the move.
So
On
have
my
a
way.
good-
Going
Okay.
there.
I hope to see you in the
Going
next
there.
video.
Going there. Let's do it. Let's do it. We're on the move. Attack.
Hey there, welcome to another video. In this video, we're going to
They're
discuss the
gone.
vertical line test. It's going to be very, very short. You've probably heard of the vertical line test before. If you haven't, that's not a big deal. I'll explain it very well. I'm going to focus more
We're
on
on the move.
why it
Take 'em
works
down.
than the how you do it. I'm going to explain both of them,
We
but
need backup.
mostly the why it works. That's how we retain
Take 'em
the
down.
understanding. So, what is the vertical line test?
We're
How
under
does it
attack.
work? And how do you do it? The vertical line test is a way that we check whether the graph of some sort of mathematical expression or equation is a function or not. So
Waiting orders.
when we look at a graph, we should be able to determine immediately whether it's a function or whether it's not. So how we do that is by understanding the interplay that
There are some
functions have
infected around
between
here.
inputs and outputs. Remember, for functions, One input gives you one output. That's it. So what we're going to focus on is why
Search
the
done.
vertical line test actually works. In order to start, we've got to
Roger.
know that the input axis, I'm not going to really talk about x's and y's, the input axis is the horizontal axis. And let's just
There's
switch that
nothing left.
around. The horizontal axis is for inputs. So with that in mind, if this is the input axis,
Building clear.
and this is the output axis, when we pick a number to plug in on
Reporting.
the input axis, it's kind of a horizontal idea, isn't it? If this was x, you'd say, all right, x equals 5 is here, and x equals negative 4 is
Roger.
over here. And we move horizontally to locate different inputs. However,
Building clear.
for any given input, the output will be somewhere above or below it. That's why our
Ready for
output
action. Search
axis
done.
we call vertical, because it has this idea that our outputs will be
Roger.
strung along somewhere along this direction, above or below each individual input. That's how the rectangular coordinate system works. You go over to an input, then you go
On
up
my
and
way.
down for your output. We
Waiting
all know this
orders.
because we can graph points at this point. So if our input axis is horizontal, and at every given input, the output will be somewhere above or below it, this vertical idea, then all we have
On
to
my
do
way.
is go over to any given input. All right, here's an input.
On my way.
And we check
Going there.
vertically how many outputs are given to us. So we look above it. Hey, is there an input? Or sorry, is there an output
Going
above
there.
or below it? Is there an output
Roger.
below? Our idea is that if one input must give us one
Take him
output,
down.
and our inputs are somewhere along the horizontal line,
Requesting
we're
support.
gonna go somewhere along that horizontal line, we're gonna pick a point, and then
We
we go
need
around
backup.
and
Running out of
above and below. Because if there's an output for that particular input, it's going to appear vertically. The output axis is vertical, therefore all of our outputs must be vertically given above or below that input. And if we find one input, great. At that point, that's a functional relationship. If we find two outputs, that's a problem. That's giving us a non-function for that input, and that ruins the whole thing for us. And this whole thing is not a function, because right here, see this? At that point, well, we have two outputs for one input. And we do this for the entire graph. So that's why the vertical line
Let's
test
do it.
works. It's based on the idea that
We're
for
running out of
functions, one
stock.
input's got to give you one output. Since inputs are located horizontally, we pick a point on this horizontal axis, anywhere that you want. And once you pick a point, basically we
Stop
do for the whole
working.
axis.
There's
Once you
nothing
pick a
left.
point on there, then you look above and below, because our outputs must be strung along vertically. If we touch our graph at more than one point, well then at that
Ready
input,
for action.
you are getting two or more
There's
outputs.
nothing left.
That is a non-function. It's giving you more than one output for that single
On my
input.
way.
We're going to practice a few of them, but that's basically the rundown here. So take a
There's
look at
nothing left.
our diagonal line. Our input axis is horizontal. I've purposely not labeled these X and Y
Reporting.
because it doesn't really matter. Our input axis is horizontal. Our output axis is
Roger.
vertical. We look at every
Infected
point
incoming.
along our horizontal axis and think, all right, well, what's going on here? Where would our outputs be
Ready for
located
action.
at
On
this
my
point?
way.
Outputs would be vertical. Well, if my outputs are vertical,
Ready for
and I
action.
start crossing my graph
We're on the
right
move.
here, that says,
Reporting.
hey, there's
Going
an
there.
output for that given input, isn't
Receiving.
there? That says, at this
Report.
input, I would
Spotted.
get that number out. At this input, I would get that number out. At this input, I would get that number out. Because for every given input on the input axis,
for action. On my
our
way.
vertical axis where it touches the graph, that would be our output. Are we touching the graph more than one time for any given one input? I know that we touch the graph 3 times.
We
but
need
those are
backup.
3
We're not alone
inputs.
here.
That's fine. And if we continue across the whole axis, no matter what, you can hear that's, hey, the output is on the axis, no problem. And we look vertically. And everywhere we touch the graph, that is the
Requesting
output.
support.
So that
Man
means
down.
we
Man
check
down.
every single time we have checked an input and we do this across the whole axis, we are
Losing
getting
men.
one output. Right there it says that one input's giving us one output, it's not touching the graph twice.
They're
The
coming.
vertical line test here says that that is a function.
They're coming.
What about the next one? Imagine some vertical lines. Imagine choosing an input here, 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 all the way
Waiting
down.
orders.
And imagine vertical lines at every single one
Take
of
him
these
down.
inputs. Those vertical lines are the outputs, or the representation of where the output would be for that given input, and where we hit the graph, here and here,
We'll get them.
Those
Reporting.
are the outputs
Attack! They're
for
coming!
those given inputs that we've chosen. Are we getting more than
Take 'em
1
down!
point on a vertical line? The vertical line represents the outputs for that input. So if we're getting more than 1 touching of a graph, more than 1 point on a vertical line, we would have a non-function. Well, gotta mess that one up. Well, no, we're not. We're getting 1 point for this vertical line, 1 point for that one, 1 point for this one, 1 point for that one. There's never a case where we're getting 2 outputs for any given input. This is our function. That one, right off the bat, what do you think? If we look at it, we go, all right, take an input here. Great. Inputs are on the horizontal axis, no problem. An output
Waiting
is
orders.
somewhere along a vertical line. The vertical axis is the output axis, so our outputs would be a vertical idea having chosen an input. You go, all right, well, here's my output axis. Like, here's where my outputs would be.
Reporting.
Let's look at the graph. There's an output there, there's an output there. Those are the 2 outputs on that vertical, oh wait, those are the 2
Another one
outputs
incoming.
on the vertical line for that input. So I chose my input, I looked at all the potential, all the outputs that we have, and we crossed the graph twice, saying for that graph, there are 2 given outputs for that 1 given input. Right there, you're done. You stop and you say, that's not a function. Because
Waiting
I
orders,
put
ready
one
for
input.
action.
I chose 1 point on the input axis. I looked vertically above and below it, and it gave me 2 points. That's not a function.
We've got them.
This one for sure is a function. We can imagine some vertical lines at all these different inputs. We think through it and go, you know what,
Let's do it.
every vertical line, you don't even have to draw them, you can imagine them. Every vertical line that we think about is only going to have 1 time
Operator.
crossing that graph. That means that every one of those
Going
inputs
there.
that I chose for those vertical lines, or every possible input on that horizontal axis is
Infected
probably a better way
incoming.
to put it. For every possible input on that horizontal axis, and I imagine an infinite number of
Reporting.
vertical lines,
On my way.
there's never a case where a vertical line is going to have 2 outputs. It's going to touch our graph twice. That does not happen here. This is a function because for every possible input, I'm getting 1 output. You know what? I need to backtrack for a second.
Wipe that sleep off your face and get to work.
Receiving.
Is it okay
On my way.
to get no outputs for an input? Yeah, and it can still be
Reporting.
a function actually. If we think about
Let's
square
do it.
roots, and a square root looks like this. Even though these
Reporting.
inputs over here are not defined for that
On
square
my way.
root, they create imaginary numbers. So when we plug in negatives into a square root
Receiving.
in this domain, there's nothing there for real numbers, so
On
it
my
doesn't
way.
show up graphically on a real coordinate plane. This does not say that you don't have a function. And this over here, for every possible input, you
Search
have
done.
1
We finished
output.
construction.
That is also a function. So don't, I should have probably mentioned that when we got to there, but don't let it be the case like, man, I'm not getting any inputs, therefore it's not a
Search done.
function. That's not the case. The case
Clear.
is this. Where you have inputs on your horizontal axis and you have something that's defined
more
for
to
your function. So where your inputs give you outputs, there's only 1. That's the idea. So where the inputs are giving you outputs, there's only 1 output and not 2. So function yes,
Construction
function
ready.
yes, function no, there's 2. Function yes, function no. For this input or lots
Search
of them,
done.
you're getting
There's nothing
2
left.
outputs for that input, you're done. That's not a function.
There's nothing left. Waiting orders. There's nothing left. Operator, we just saw something grisly,
Lastly,
but
how about the
potentially
vertical line
useful.
test?
The
Can a
infected
vertical
are
line
eating
pass
their
the
own.
vertical-
We saw some of them
Can
inside a
the
basement
vertical
they
line
couldn't get
pass
out
the
of.
vertical line
There were
test?
corpses of other infected
Well,
that
let's
had
think
obviously been eaten.
What if I take an input over here? Are there any other inputs? Or
Leave
some
them to
outputs
rot
for that
down there.
input? That's fine.
Roger that.
If you-
Reporting.
if you're not worried about inputs not giving us outputs, worried about where the inputs are giving us outputs, they're
nothing
giving us
left.
only 1. So we check all these. Hey, there's no problem with
Clear.
any of these vertical lines. But as soon as I get to that input right there, I say, hey, what's the 1 output for that 1 input?
There's
You go,
nothing left.
wow, there's lots of outputs for that 1 input. In fact, every point vertical is an output for that input. That's a non-function.
On my way. Search done.
And I hope that makes sense to you. I hope that you're seeing the interplay between inputs and outputs
Building
on the vertical
adaptive.
line test, that we're checking inputs. That's a horizontal idea, so you locate one, and you look above and below it for an output. And if it has outputs, there can only be one output from it. So yes, yes, no, that's a problem. Yes, that's fine. No, that's not fine. No, that's not fine.
Let's do it.
Vertical line does not pass vertical line test. Here, this is certainly a function. So a square root says, I'm not giving any outputs, therefore the vertical line test doesn't really apply, but where I get outputs from my inputs, there's only one output for every given input. That's how the vertical line test works, that's why it works. And so we're going to be using that from time to time just to check to see whether we have functions or not, or when we're graphing, like especially piecewise functions, to make sure that we're not actually accidentally overlapping our graphs, because that would
There's
be a
nothing
function.
left.
So I hope it makes sense. I'll see you for the next video.
Building complete. We are out of resources.
Hi, welcome to another video. Hope you're doing well, hope you're ready for something we're going to talk
No more
about
to find.
frequently, which is graphs. And right now, in this video, we're going to learn about some features of graphs, namely points, domain, and range. So while this isn't going to be a whole long, exhaustive list of
Search
things
done.
we can do with graphs, it's really nice to be able to start with how graphs work and what really is being asked. Because some of the terminology, while it's not difficult to do, can be a little
We're on the
confusing.
move.
So we're going to talk about how to find points in a graph, what they mean when they're asking all of these questions. We'll talk about domain and range quite a bit. I'll also give you some very
Waiting
interesting
orders.
examples
Building
where
clear.
students get confused on why in the world the domain is this, and what that really means for a graph. And it's very important to get what the domain is
Clear.
correct in your head. So we'll talk about that for a little bit. We'll also talk about how to do this without a graph if you need to find this information without the actual picture of the
No
function
more to
itself.
find.
So that's the lesson
No more to
for
find.
this video, and then we'll continue next time to talk about some more features. So let's get
Search
right to
done.
it. When we talk about graphs of course are this representation of every point that satisfies a function that you're given. So we have an infinite number of points, but sometimes what's going to be asked is, well, what about some specific
more to
points?
find.
So what about f of 0? What in the world does that mean? Well, what that is talking
Clear.
about, when they're asking you f of 0 or f of negative 6, it says
Ready
the
for action.
function itself is going to give you an output value. We plug in a value, we get an output out. So input, output. And this is saying, what is the function's output value? So the output of the function equals what when your input value is 0? In other words,
Waiting
all
orders.
this is really asking you to do is to complete a point. So if we look at our graph and say,
Wrap it up,
like complete a
folks.
point,
Time to
if
call
the
it a day.
input is 0, it's saying, what's the output of the function given your input is 0?
Reporting.
It's saying,
Roger.
complete this
Operator.
point. Here's your input of 0, find me the output. So
Receiving.
we look at our graph and go,
On my
okay,
way.
here's my input, my x is my input axis, here's my input of 0, my output of my
Operator.
graph is 0, 5.
On my way.
Notice how the point's given for you, you just have to find it. So this is saying, complete this point really, if your input is 0, your output has to be 5 for this given function. So this answer would be 5. You can just complete a point, and that's what that's asking you to do. Same thing with f of negative 6. It says, find me the output's value, the output of the function at an input of negative 6. So we go to our input axis, our x-axis, we go, here's our negative 6. Let's go up or down to where we meet the function. Let's find the point. Let's complete the point with an x in an input of negative 6. So here's negative 6, here's negative 6, negative 3. So really it's saying, if you want to complete this point, just find the point on the graph that has an x value of negative 6,
Reporting.
and the output would be negative 3. That's what we're talking about here. So really, this is asking you to find points on the graph. It says, find me the output when your input's 0. Find me the output when your input's negative 6. Find that function's output. Say, complete the point with an x value of 0, negative 6, respectively. Kind of similar is this f of 3. So let's find f of 3, where that would be, and just determine whether output is positive or negative. So anytime they're talking about f of something, f of x, f of whatever, it's an output idea. So it's saying, I want you to look at the y value of whatever x value you're inputting. So find me a
There's
point on the
nothing
graph
left.
that has an output, where the output is given by an input of 3. So in other words, we're going to go to the input value of 3. So f of 3. Here's our x value of 3. Find where the function is. Is it above or below? Well, if we had to put a point on this graph where we would have 3 comma something, an input value of 3 and then whatever output, it'd be up here somewhere. Well, it looks like it's about 4. It's not asking me whether it's 4 or not. It's asking, is the output value positive or negative? And that's what it's saying. It says, given an input value of 3, what's the function doing? What's its output? Is it positive or is it negative? Since we're above the x-axis, all of these output values are positive. This would just be positive.
Roger.
For f of 8, we do the same thing. We all right. Well, tell me what the output is. If our input is 8, the function's going to give us some sort of an output for the input of 8. I'm going to go to my x-axis for an input of 8, and it's asking, is that output value positive or negative? Well, when we look at 8, it says I want to complete a point where we have 8 comma something. It's actually done for you. Here is 8 comma negative 3. You know what? All right. Well, I could actually fill that point in. It's negative 3. It's given to me on that graph. But what we're concerned about is the output value positive or negative.
You're out of resources.
Below the x-axis. Well, our y values are all negative here. So, given an input of 8, f of 8 is asking you what's the output value for the input. So basically, complete the point. In this case, it's just asking you, is that output positive or negative, or could it be negative? Hope that's making sense so far. That's kind of the basics of how they ask you what points are in a graph. They say, tell me the output value for an input. It just looks a little bit funny. They're not asking specifically like that. We can also do things like, what values of x is
Waiting orders.
0. Now, here's where we really have to understand what the function notation means. This says, I want you to look for outputs of 0.
Inspection cleared.
Not inputs of 0. I'm not plugging in 0.
We're on the move.
I'm letting x equals 0.
We're on the move.
We know that if x is 0, our output's 5.
Waiting orders.
We're done. What this is saying is, think differently. Think about every time where you have an output of 0. So really, you could do this. You'd say,
Roger.
I want to find points where my output is 0. Notice how points are set up.
On my
Points
way.
are always set up x, comma, f of x. And now I'm saying, I want you to find me some points where this number over here is 0. How many points do that? Well, all of those points, now get this is important, all of those points are going to be on the x-axis. All of those points are going to say, hey, here's an f of x of 7, 6, 5, 4, 3, 2, 1. Here's an f of x of 0. This whole horizontal line represents points where your output would be 0. And this is saying, I want you to complete points. What's your x? When your output is 0, it's saying find x-intercepts. This is just a way that they have you do that. So when they say find all the values where f of x is equal to 0, it's saying find all the values where your output is 0. Find all the values on the x-intercept, on the x-axis. Find all the values that are x-intercepts. That's what that's saying. So it's going to put this point. Well, there's a few of them.
Waiting orders.
We have negative 4
Rising
and
grind.
output 0.
Going there.
Hey, that's the x value where your output 0. 6 where your output 0, and 10 where your output 0. So for what x's is this output 0? For what x's do we have x-intercepts?
On my
We'd
way.
say there's negative
We need
4,
more resources.
6, and 10. Those are the x values where we have an output of 0 on our graph. So we have this negative 4, that's on the x-axis. That has an output of 0, and 6 and 10. You can write it like this. Me personally, I really prefer to write points, so I'd probably take this a little further and say, well, we have negative. They don't specifically ask this, so they say, well, for what x value is that? I just like to make sure that my students know that those values are giving you x-intercepts, and x-intercepts are points on a graph. They really are. Now, we oftentimes just put x's, and that's totally fine. We all understand that x equals negative 4 is now an x-intercept. It said, hey, your output's 0. You're on the x-axis. No problem. X-intercept. And that's okay. But I want to make sure you understand that.
Vehicle taken over.
So negative 4, 0, 6, 0, 10, 0 are x-intercepts on that graph.
Construction ready.
The x-axis. Okay, I hope that's making sense. I hope you understand right now that really this is just asking you to complete a point where your x is 0, find the y. Your x
Operator.
is 6, find the y of x. Your x is 3, is the output positive?
On my way.
Your x is 8, is the y value.
On my way.
This is different. This is saying,
Sir, we stumbled upon a
y value,
building which
x
looked like a
value is 0.
hobo
Find the
hostel.
x
Search done. except it was reeking of infected. Each room had a makeshift bedding made of rags, mattresses, and other stuff things. One room also looked like some kind of storage with random items. Did they start to create fires or something?
Let's do it. There's nothing left.
Search this place.
We're on the move.
Oh, well,
We're on the move.
There's nothing left.
We're greater than 0 between 0 and 5, obviously, because that's how
Let's do it.
Roger.
When we understand functions, what
Let's do
functions deal with?
Roger.
Functions deal with almost exclusively, and only within
Let's do it.
range,
Going there.
this idea of intervals on the x-axis. You see, x's are independent variables.
No more to
X is what
find.
drives everything in our function. So when we think about that, we think, here's how this is really better worded. For
Receiving.
what interval of your x-axis
Let's
is
do
your
it.
graph
Clear.
positive? For what interval of your x-axis is your graph above the x-axis? That's what this is asking. So when
Going
you think
there.
about this, you can't go this way. All right, for what interval on the x-axis am I above it? Well, let's think about it. Is this range of your function, or sorry, this I'll say,
Search done.
is this piece of your function above the x-axis? Is it positive? Well, no. We know
Building
that the
clear.
graph is above the x-axis, starting probably right here.
We are out of resources.
Right here. And what we've just done is marked off the piece, the interval of the x-axis where the function is positive. That's exactly what it's asking. Find me the x values where your function's positive. That's this interval of x's. That's what that's asking.
Going there.
It says, give me the piece of the x-axis where I'm above the x. It's not a this way idea. It's a x-axis idea. Almost everything we talk about is an x-axis idea. We find x-intercepts. Y-intercept, we got that, but we have an x interval here that says for the interval of numbers between x
On my
equals
way.
-4 and x equals 6, my graph is going to be positive. And we have two ways to write that. So we're going to say, all right, you know what? One way I could write this, for what x's is my function positive? Well, you already know how to find positive, right? You knew that at 3 we were positive, at 8 we were negative.
Let's
This
do
is
it.
saying find a whole range of them, whole interval of them. So our interval from -4
Roger.
to 6 is going to give me positive outputs. The way we write that is from -4 to 6.
Ready for action.
Those are the
Search
values
done.
of x's, right? We said, hey, all this whole range from -4, x is somewhere between here to 6, we're going to get positive outputs. That's exactly what the question's asking you. The other way that we can write this is with something called interval notation. In my opinion, it's not the best notation because it ends up looking a lot like points, but it is one way that we can represent this and you need to know it. So the other way that we can write this is, hey, you know what, from
No more
I
to
want to
find.
write the x values from -4 to 6. I can also write it up like this.
Work's
The
done.
interval of
Search
the
done.
x-axis where we have positive outputs
Building
is from
clear.
x equals -4 to x equals 6, but not quite equal.
Ready for
You
action.
see, if we let this equal, notice, if we let this equal, I'm really not positive at this point right there. At that point, I'm not positive. I'm negative, I'm 0. Well, that's not what this is asking you. This is saying, where's
Search
your
done.
graph strictly positive? Not equal to 0, or we would include the -4, we would include the 6. That's not what it's telling you. It's saying, I want you to be strictly positive, and that says, well, I
There's
can't
nothing
We are
really
out of
include this
resources.
x-intercepts, because add an x-intercept, I'm equal to 0. And I don't want to be equal to 0, I want to be positive. So we can't include that. For that reason, we show this interval with what are called parentheses. This represents the same exact thing. It says, hey, the x values for which your function is positive is -4 to 6, but not including those two endpoints. Or -4 to 6, but not including those two endpoints. To include
Clear.
them, we use a bracket. And I'll show you that when we talk about the domain. Okay, how about you should try this right now. What about the function?
Receiving.
Where's the function less than 0? Oh, you know what?
Reporting.
I missed one, sorry. Where's the function greater than 0? We have one interval, I talked about that, but there's also this other one right over here. You go, well, yeah, we're not
Receiving.
above the x-axis here, that's below, that's outputs
On my
that are
way.
negative. We're above the x-axis where our outputs are
On my
positive
way.
from -4 to 6, and not between 6 and 10, but then from 10 to 11, we're also positive. So the way we're going to write that, write this all together, is we have this, we also have an interval right here from 10 to 11. This little interval, not up and down, but x-axis wise. We say The x values that are giving us positive outputs are also found from 10
On my
to
way.
11. So this is one way we can write it with this inequality notation. We can also say, all right, so interval notation, we go -4 to 6, no problem. And then we also go from
No more to find.
10 to 11. And that little u there is a union. It's saying this interval combined with this, or this interval or this interval, are going to give you values that are positive. Our outputs are positive. Hope that you're sticking with me here. I hope that's making
Building
sense
clear.
to you. You're seeing the interplay between the x intervals and the outputs, and we're pretty much always talking about the x interval, and we're talking about increasing and decreasing.
Building clear.
We haven't done that yet. When we're talking about positive versus negative functions, we're talking about domain. We'll be getting that in a second. All right, now we're ready to go ahead and look at what interval of x-axis is our function below 0. So same question, only in reverse. And you can probably see it right now. You should be doing this.
Clear.
We notice that our function is below the x-axis here, and again over here. What we're going to look at it is what interval of the x-axis
No more to
gives us
find.
outputs that are negative. What interval in x-axis has my graph below the x-axis? Well, that looks like it's from -6
Search done.
to -4. Same idea.
Operator.
If we're if we're not above, and we're not constant, we're not at 0, then we're below. So the intervals that we didn't just mark off for being above the x-axis probably are going to give us below. That would be -6 to -4,
We're on the move.
and we do it both ways.
Reporting.
So -6 to
Reporting. Clear.
-4 give us an interval on the x-axis
Clear.
where we are negative. Also, from 6 to 10.
Search
That
done.
gives us an interval on the x-axis where outputs are below the x, or negative. If we want to write interval notation really similar, we're going to do -6 to -4. We're going to do parentheses because,
No
again,
more to
we're not
find.
equal to. We're not saying less than or equal to. We're saying strictly negative.
Search
If I
done.
let the equals go, I'd include those values, but here I can't include the values -6, -4, 6, or 10 because that would give us a 0.
Clear.
So
No more to
I don't
find.
want to be equal to 0. I want to be strictly less than that. I want to be negative.
Building clear.
We'd also go from
Clear.
6 to 10. We show that with parentheses and are just strict inequalities there of less than.
Search done.
That's got to make sense for going any further. We got to understand how to find some points and what they mean by that. We got to find positive and negative and what they mean by saying,
Building
hey, what's
clear.
your output value when your x is such and such. We got to really
No more to
understand what
find.
this is about. When they're saying f of x equals a number, they're saying I want you to find
No
x
more to
values
find.
that yield that output value. So this is saying I want you to find x's when my output is 0. No problem. This is saying I want you to give me the interval
No
of
more
the
to find.
x-axis where I am positive, or the interval of the x-axis where I'm negative. It's not an up and down
Roger.
idea. Now we want that to be the case. It's an interval of the x idea. It's always from this x to this x. All right, moving on a little bit. What the domain means. I think
No
we
more to
talked about
find.
this in another video. The domain is this idea of what inputs I can plug into a function and get an output. Well, graphically, what that means is what section of the
No more to find.
x-axis does my graph cover? What interval of the x-axis does my
Slappers,
graph
wake up and do your
cover?
job.
That is what the domain means. So
Building
it's a
clear.
very one-dimensional back and forth idea. So domain says,
missing
all right,
resources.
look at my function, tell me the entire interval the x-axis this thing covers, and we see it right away. The interval that this graph covers on the x-axis, so our domain, our inputs, our x-axis is our
Operator.
input axis, says our graph covers what portion of that? Well, it's from -6
Operator.
to 11. That's the section of the x-axis from here to here, and it covers all of this.
On my way.
Okay, just move that in.
Waiting orders.
So that is what the domain means. It says just give me the inputs. What are inputs? Well, x's. What that means is that what are the values that are giving me actual outputs? All right. Well, that
curious
would
what
be
this
a
game looks
section
like
or
for, like,
interval of the x-axis
Detroit.
that's giving me some sort of graph. In other words, what's the graph cover?
There's
The
nothing
graph
left.
covers on the x-axis from -6 to 11.
Going there.
So we can write it like
Search
this.
done.
We have that x such that we remember the set builder notation. X such that x is between
There's There's nothing
negative
left.
6, and 11. Notice the difference here. I used something that I didn't use over here. Over here was strict inequalities because we wanted to be less
On
than
my way.
0. We didn't want our function to equal 0 or greater than 0 as the case would be. Here we're saying, no. Give me every value of x that gives
There's
me an
nothing
output.
left.
Well, does negative 6 and does 11 give you an actual output? Yes.
Operator,
And so
we
have
found
to
another
include
layer.
these values, and we
There were a
did
lot
that
of empty
because
cans and
less
other
than
food
equal
containers,
to.
which looked like they had been
We're on the
smashed
move.
open with stones. Can the infected actually get such ideas? Bastard's getting smarter day by day.
No more to find.
I want to include that. I want to make sure that my
Search this
location
place.
has an equals, saying yes, this value is included in my domain. In my setting,
Boss,
it's
the
an
infected,
actual
search done.
seem to be stacking
on those
food.
values.
We found a
So
hidden
there
stash of
are-
unopened cans in their lair. Can you believe that? They're literally hiding stuff.
Interval notation is a-
They're not as mindless as we thought.
That's what that bracket is. Range is the idea.
Take them. We can always use some food.
Because we can go back and forth looking at it vertically. Domain's a little bit easier because we're looking at the x-axis saying, hey, you can only cover it at one point. But with range, it's a
Operator,
little more
going there.
challenging because we can
Search
cover,
done.
cover the
There's
y-axis
nothing
and cover it again. We don't necessarily have to be a one-to-one function. X-axis is just
We need more
vertical lines,
resources.
passes as a function. Every single vertical line's going to cross our graph one time, no matter what. Like x equals 3, okay, that's only one output value. And so it's kind of easy to see, hey, this graph covers
We're on
this
the
part
move.
of my x-axis. Range says, tell me what section, what interval of the y-axis or f of x axis my graph covers. My graph gives me outputs there.
Operator.
So we're looking on both sides here, figuring out, well, what section of
We're on
the
the move.
y
Ready
does
for
this
action.
graph cover? I'm only going on the y. Notice how on the domain, I
On my
didn't go
way.
off of that x-axis at all. Same thing with the range. I cannot let my pen move off of this y-axis. So I'm looking, what's my lowest
my way.
value on the y? What output does that cover? Well, it covers down to -3. All of these outputs are covered somewhere. It doesn't matter how many times they're covered. I don't care. That's what makes it a little challenging, is making sure you're covering it. And then, okay, the highest value we're getting is 5.
Reporting.
So the interval that we cover on the y-axis
On my way.
is from -3 to 5. That is what the range means. And we can use y, we can use f of x.
On my way.
You'll see both.
Let's do it.
Here we probably should use that f of x, but I want to make sure I give that to you.
There's nothing left.
And we'd say all the
Time to
output
sleep,
values
everyone.
can be found between -3 and 5,
Roger.
including those. Notice how we actually attain a
Search
-3.
done.
We actually attain a 5. So we have to show that with that
There's nothing left.
less than or equal to. We also have to show that with brackets. Okay, now how about x-intercepts? Well,
Building clear.
wait a minute. X-intercepts. X-intercepts are where the function outputs will be 0.
Clear.
The function outputs will be somewhere down here. We've already done that. When you find f of x equals 0, you are finding x-intercepts.
No more to find.
So this is a redundant question. So we'd say, hey, where our function's value was 0, where our output height was 0, we'd be on the x-axis. We already found that x is where that's the case. So
We are
this
out
is
of
basically
resources.
kind of reinforcing that, hey, do you know these numbers over here? Yeah, that's what you're finding. So your x-intercepts are -4, 0, 6, 0, 10, 0.
Let's do it.
Now, can the function have more than one x-intercept? It'll still be a function.
Chief, did you hear that? There must be hundreds of them.
Can a function
I have a bad feeling about
have
this.
more than one y-intercept and still be a function? No. That would
Okay,
be
get ready to defend the zone.
Okay, one input needs to give you exactly one output. So your y-intercept there needs to be
Waiting orders.
if there even exists one. So
Operator, we found
y-intercept is
something
where we
suspicious.
cross the y-axis.
There's a
We
large
cross the
piece of
y-axis
dried
one
meat
way,
here with a
so
piece of
that
rope
puts
around
that
it.
axis.
It's attached to a counterweight.
Notice
Going
how
there.
This
every
seems to be a
single
trap to catch
y-intercept
something.
has zero.
Maybe humans, maybe animals, or maybe even the infected. Somebody must have set it up not too long ago.
Alright, last
Ready for
couple
action.
here. How many
Receiving.
times
Take him
does
down!
the y
Make sure it's
equals
disarmed and
line
try to find out more about
cross the graph? Y equals 2, let's see. Y equals
operator.
32 times. That's it. That's
Let's do it.
Receiving.
Let's do it.
Ready
Last
for
one.
action.
Students get super
Roger.
confused about this. You go, I
Building
understand
clear.
the X intercept idea. You go, yeah. If I said equal 0, I'm just find out where we cross the X-axis. But how I introduced that to you, I said, really,
There are
think
some
about
infected
this
around
as
here.
you're trying to complete some points. Trying to complete a point where your output is 0. Find me the inputs. I don't know the
Reporting.
X. Find me the input when your output's 0. Okay, here's my output of 0, output 0.
On my way.
And then an input of -4, an input of 6, and an input of 10, and that would give me my output of 0. This is doing the same thing. It's saying, for what X does f of x equal 3? It's saying complete the point where
Roger.
the output is 3. Every time you say
We're on
f
the
of
move.
x equals 3, it's saying I want that output to be 3. So do we have some points where we have a 3? Well, let's see. 3 is positive. 3 is going to be above our x-axis somewhere. So I'm looking above here, looking for my y value or f of x value of 3, and I'm saying, oh, wait a minute. Hey, here's a y value of 3. Right there. Here's a y value of 3. Here's another y value of 3. Oh, there's 2 points.
Roger.
Is it okay to have 2 points? Yeah, sure. It says for what axis does this work? It's okay to have more.
Hostiles inbound. Support.
We need
In
backup.
our case, this says -2 would give me an output of positive 3, and 4 would give me an output of 3. So I'm looking for the x value that's causing my function to be
Losing men.
Casualties.
Man down. Man down.
Casualties.
Get off me. Ah!
If you didn't have these points listed, it'd kind of be a guessing game unless you have a rectangular coordinate showing you this. So we have to sort of guess, here's my output of 3, and we go over and say, output of 3 has a
The door won't hold much longer.
my output of 3 also has an input of -2. You have to do it that way. Last one you should be doing on your own. Give me some x values, or complete the point that says I want the function's output. This is an output of -3. So I'm going to say, looks like 2 points. You should be finding those 2 points right now. Just thinking, maybe thinking in your head. There's 2 of them. You say, well, what's an input value that's going to be giving me an output of -3? Or find the input that gives me the output of -3. Here's -3. We could go over. We hit our graph here. A point's already listed for us. We say an input value of 8 is what's giving me the output. This way, an input value of -6 is what's giving me the output. We completed that point. Input value of -6. I hope that's made sense. That's a lot about graphing as far as what the points mean, what they mean, what it looks like to ask what a point is on a graph. And that's what that's doing. Saying, find me the input if I give you an output, over there. Find me the output if I give you an input. Quickly, those points. We talked about what x-intercepts are, what that looks like, what that means when they're asking you f of x equals 0. We also talked about domain and range. So the section of the x-axis your graph covers, that's your domain. Section of the y-axis your graph covers, that's your range. I'm going to come back in just a second. We'll talk about some sort of tricky problems with domain and range. We'll get more into that. I'm not going to ask you about points anymore. And then I'll show you how to do this stuff without a graph. All right, let's get after it. So on these 4 graphs, we're just going to be talking about domain. We're talking about range. Just making sure that we really understand that. It's a big deal. So what the domain means is the portion, the section, the interval of the x-axis that your graph covers. So we're just looking at the x-axis. You should know very quickly. What this says is that, hey, you know what? If I look at my first graph, the section of the x-axis is from here to here. I don't care that it's pi and negative pi. It's looks a little strange for us, but it's just a trig function. We'll talk about that when we get trigonometry, no problem. But our domain, and that's huge to know what the domain is for trig functions, is from negative pi to pi. The interval of the x-axis that my graph covers is negative pi to pi. Now think, am I going to be using equals and brackets or not? Well, the points are included. So I would say we have x's from negative pi, including that value, to pi. Interval notation would just be negative pi to pi with brackets. The range, the interval of the y-axis, or f of x-axis, that our graph is covering says, well, we have the smallest value of negative 1 and the largest value of 1, and we're covering everything in between there. So for our range, we have y values such that we're going from negative 1 those are always in order to 1, including those values because those points actually exist there. And interval notation says from -1 to 1. I hope that's making sense. The interval of the x-axis that our graph covers, that's the domain. Interval of the y-axis our graph covers, that's our range. Now, if we take a look at this one, I'm going to do this one next. The interval of the x-axis that our graph covers, some students get really confused with arrows and go, oh, I'm going up, I must follow this up. Think about the x-axis only. So, if you think, I can only move my pencil across this, just one-dimensionally, not two-dimensionally, just one-dimensionally, how far will I eventually go? Well, eventually, my pencil's going to have covered everything in here, so this whole section, but it'll cover everything this way, and it will eventually cover everything this way. Notice, this graph is continuous, it's shown to continue like this. It will eventually, though, cover the entire x-axis. So, because the domain is the interval of the input axis, our x-axis, that our graph covers, this graph will ultimately cover the entire x-axis. That needs to make sense to you. So this is everything from negative infinity to positive infinity. Are we sure of that?
To all circles, the effect will decline.
We could write negative infinity less than x less than infinity.
Chief, this is the same transmission we received before, but the signal is even weaker. Our walkie-talkies are not powerful enough for long-range communication. We have to build a large antenna. A local library or university would be a good place to search for information on how to make it work.
Or we simply put all real
We're missing
Now,
resources.
is the range going to cover, sorry, is this graph going to cover the entire
The option is in the clouds. He covers
This is an exponential function. I tried to write e to the x for you. You probably have seen that at some point.
We're running out of
but
resources.
This is at least an exponential function. And it has a horizontal axis. It's coming from this
Let's go
way.
there.
It came from being really close to 0. And if you look at it going to the left, it's going to get really close to 0 as we approach negative infinity. But it never hits that 0.
Waiting
So
orders.
as far as the range is concerned, we're not covering the entire y-axis. We're basically covering
On my way.
from
Ready
0
for action.
upward.
Let's do it.
Remember, this is a one-dimensional idea. X-axis, you can only go back and forth. Y-axis, you can only go up and down. So we're covering from 0, but not including it, and then to infinity. So our y values are y such that y is greater than or 0 is less than y
Ready for action.
to infinity. We can't include the 0 because we never actually attain it. We just get really close to that. That idea is super important for us to accurately find the domain in problems like these two. With that open circle, what's that mean? I'll talk about that in a second. Or from 0 to infinity. So the section of the x-axis that our graph covers the domain, we got that down. Y-axis is our range. Now when we get to problems that look like this, they're a little funky because what that open circle means is that that point is missing. We get right up to it, it's called the removal of discontinuity. Most of the time in calculus we call it that. This says, yeah, there's an endpoint here, but this endpoint is missing. So how in the world are we going to define our domain, the section of our x-axis that our graph covers, if we're missing a point? Well, let's look at it. What section of the x-axis do we actually cover? I think we'll all agree, well, on the x-axis, we're only going left and right, one-dimensionally. It includes everything from here, including that 0, and then it goes all the way up to the 4. It includes things like 3.9, 3.999, 3.99999 for a really long time. It just doesn't include the 4. Think about it. That's very similar to what this did. This would have values of like 0.00000000001 as an output. It just would never attain the 0. How we show that is with parentheses. We say it's really close, but it never really gets there. This is really close to 4, but it never really gets there. Alright, it's going to be a parentheses around the 4. It says that we get really close to it, as close as you can get without touching it, but we don't include the actual value. So that's that point. So close, it doesn't include 4. You don't stop at 3. You don't stop at 3.9. That's not nearly
We're on the
close.
move.
We're way closer, and that's what the parentheses tells us. It says that we're very close, but we just do not include it. It's basically excluding one point, just the end. So our domain here says two ways. Number one, the section of the x-axis that our graph covers starts at 0, and we include it. There's an actual point there, and it ends at 4, but we disinclude it. There's not a point at the 4. Do you notice the two inequalities we're using? We see, yep, we actually can attain the 0. The section x-axis has a point there, and then we say, well, up to 4, but not including that, because at that 4, we're missing the point. Don't miss that. So we get really, really, really close, but that point is missing. So the section of the x-axis that we're actually covering stops. It gets really, it actually doesn't really stop. It gets really, really, really close to 4, as close as possible to that. Or interval notation says 0 to 4, with a bracket around the 0, because we do include it on the x-axis, but not 4. The range is quite similar. You probably can do this on your own. As far as the range is concerned, the section of the y-axis that we're covering is from 0 to 5. So look at it this way. So just turn your head like that, and we have another number line saying, yeah, we're going to erase that. We are including that 0. Sure, that is an output value that we actually attain, but we don't really get an output of 5. So close to it. Input of 4, we almost get that. Output of 5, we almost get that. We're so close, 4.99999. But to show that, we say that the section of our y-axis that we actually cover is from 0, including it, but up to 5. Okay, and the last one, maybe try it on your own. I want you to think about what section of the x-axis your graph covers. What section of the y-axis will your graph ultimately cover? As far as the x-axis, this graph has this is like a logarithm, this graph has a vertical asymptote, so while it gets really close to 0, does it ever actually touch x equals 0? Notice, domain is a strictly on the x-axis idea. You just look at this graph saying, hey, if I superimpose a graph on my x-axis, it's going to cover from here all the way up to here. That's all we're doing. That the end of the section of the x-axis your graph is covering is this section of the x-axis. Well, that's from
Get up,
0
everyone! Work's waiting!
to 7. But I can't include either the 0 because I never get in. I'm not allowed even to put an input in there. There's no output from that 0, and so that's not a valid input because it's not giving us an output for this graph. Also 7, I can't include the 7 because it's not a valid input that's giving us a valid output. It's not giving us an output, so we can't include it saying, hey, you know what the domain is? The domain is a set of inputs that are giving us outputs.
Sir, the people have reported hearing a lot of noises coming from underground. They're afraid that it could be infected moving through the sewers and tunnels. We need to bolster our defenses and be ready to attack from within, too.
The range, the section of the y-axis of the graph.
We'll be ready.
This is going all the way down to negative infinity. So we're going from negative infinity all the way up to 12, but we don't include either one. So we can't. It says there's not an actual output of negative infinity because you can't ever get there. There's not an actual output of 12 because that point is missing, but we get really close. And that's the two ways I can explain the getting there idea. We don't include it. So we have some y values that are from negative infinity, and we get almost to 12. That's what that means. Or we get to a valid output that's just before 12, but we can't include that because 12 is not a valid output.
There's nothing left.
And likewise for interval notation, negative infinity.
We're missing resources.
Oh, I hope that's made sense. I hope that I've already done with graphs for now. I hope that graphically you understand the domain and the range idea. Students get really confused with domain and range. They don't understand what it is because it's never taught to them very well. Like, hey, what domain is for a graph? It's just the section of the x-axis that this is actually covering.
Let's do it.
If you have inputs that are not giving you outputs, or not giving you valid outputs, then you must not
Operator.
include them. And we do that with the parentheses. Lastly, what if you don't have a graph? Can we still do some things if we don't have a graph? Yeah, it might not be as easy, sometimes a little bit easier, but let's go through and see if we can find some things that are similar to what we've done, such as, hey, can you find points? Can you find points where you have an output given on an input? Can you find the domain x-intercept and y-intercept. So some of the big ideas here. If I ask you for f of 1, remember what that means? It says here's f of x, f of an input value, and I want your input value to be
Infected
1.
incoming!
Okay, so what I'm asking you to do is complete the point where your input value is 1. That's what I'm asking. If I plug in 1, if I evaluate for 1, well, that's doing it. This says find me an output value for x. Here's the formula for doing that. Find me an
Another one
output
incoming!
value when x is 1. So 1 plus 2 is 3, 1 minus 6 is negative 5. We have negative 3/5.
There's nothing left.
Just asking you to complete a point, just like we did for graphs, but instead of a graph, a picture of the function, I'm giving you the actual formulaic algebra.
Infected incoming!
That. So you
We
plug
need
in
more
1, you get
resources.
an output.
They're trying to get inside.
Now, this part of the part's fine.
Our building
What
is
if I
under
say,
attack.
now I don't want you to find an output given an input. This says I want you to find the input.
Man down! Man down!
Your
Everybody
inputs
get ready.
give you your total output. So it says the output of a function, here's my function, where my input values are x. Here's, I want you to find me the output when the input value is 1. Plug in 1. It says, I want you to find me, oh wait, I want you to have an output of 2. Find me the input. It says, I don't know my x, I'm looking for my input value when my output is 2. Look at the way that your function is designed. It's designed very well. It says, can you replace f of x with 2? Well, wait a minute. Here's f of x. Can I replace this whole thing? It says, this piece, your output, this is 2.
Receiving.
So we'd say, all right, if f of x equals x plus 2 over x minus 6, and I tell you that I want my output to be 2,
Search
I
done.
literally say f of x is x plus 2 over x minus 6. Now f of x is 2. I can replace the f of x with that 2. And then I can solve for x. We're going to spend some time on this
Reporting.
because it's incredibly important. We get it with finding inverses. We do this a lot with exponential functions. We talk about it sometimes on even versus odd and domain. So I need to show, inverse, a lot of inverses, not even.
Let's do it.
So here's how to solve an equation when you have variables in more than one spot in the equation. Number one, this is a proportion. This is a rational equation, and so we can and need to multiply both sides by
We're
the
missing
LCD. We're
resources.
going to do that. So we're going to multiply by x minus 6 on both sides of our equation, but we're only doing that so that we can cancel out that denominator. We want to be able to do that. And yes, we're going to distribute. 2x minus 12 equals x plus 2.
Wrap
In
it
the
up,
future,
folks.
what's going
Time
to
to call
happen
it a
is
day.
we are going to have 2 variables up here. And I want to start this idea right now so that I can kind of preface your learning when we get way in the future, right? Here it's going to be fairly easy
Reporting.
because we're just multiplying both sides by your denominator. But in the future, I want you to look at what would happen if we had a variable here instead of a number. So think about what you do now, because this is something you know
Ready
how
for
to do,
action.
and then we're going to apply it later to something you don't know how to do. So please focus here. How you go ahead and solve this, you all know that you're going to subtract your x from both sides and you're going to add your 12. Why? Because you want to get all the terms with the variable you're trying to solve for on one side,
Ready for action.
and all the terms without that variable on the other side. The same exact logic you know right now is going to work later for inverses and later with exponential functions and solving those things. So please keep in mind what we're doing here is you're getting rid of your fraction by multiplication, yes. You are distributing, yes. But then you're trying to group your terms with x on one side and non-x's on the other. Just keep that in mind because it's going to come back at us. So x minus 12 would equal 2. Yes, we add our 12, we get everything that's not an x on the other side. That's x would equal 14. Right? Well, you know what? You can check your work, couldn't you? If you plugged in 14, it should give
Search
you
done.
We're running out of resources.
14 plus 2, that's 16. 14 minus 6, that's 8. 16 over 8 is 2. So we know that we're right. We've completed a point. In fact, you can show that. This says, I want you to complete a point
Morning,
Waiting
everybody.
orders.
Time to earn your living.
where your output value is 2. Have you done it? Yeah, you have 14. You've completed the point, and that's what that's asking. For domain, I'm hoping you remember domain. Remember that domain, right now there's 2 issues with
Receiving.
functions. We have square
On my
roots
way.
or even roots, and then we have denominators. And if we don't have those, generally our domain's all real numbers until we get the logarithms. So here we go, we don't have any square roots, that looks fantastic, but we do have a denominator. What we know about denominators is that if denominators equal 0, we've got a big issue. We have an undefined value. And so what the domain is the set of inputs that give you defined real number outputs. Well, x equals 6 would give you an undefined value, and an undefined situation. And so we say, well, you know what, if my denominator equals 0,
Operator, the moods in our zone are terrible. People are on the edge, and if we don't do anything, they will start leaving soon.
It's not defined. It's an input where the output is not defined.
We'll do whatever it takes to keep people here.
We could disinclude that. So our domain is x value such that x does not equal 6. If you forgot about interval notations, a little bit worse than that. So if 6 is the only number that doesn't work, I'm disincluding it, then really the domain is from negative infinity to 6, and I'm disincluding that. Remember how parentheses disinclude a value. So you can go up to 5.
We are out of resources.
And then from 6.0001 or whatever to infinity, but you're just disincluding the 6. X-intercepts are found very similar to setting your function's output equal to 0 or equal to 2. So let's see, what's x-intercepts?
Stop working.
Building clear.
Down for some rest.
To be 0. That's how we found them on a graph, and that's exactly how we find them now. It's a little bit easier than this. I'll talk about why in a second, but I need you to understand the idea. An x-intercept is where the height of your function is 0.
Incoming!
So if your height of your function is given by your output, set your output equal to 0. This will
The door
always
won't hold much
give you
longer.
x-intercepts in any sort of a function. So if we say I want my output to be 0, well that is
The door
an
won't
x-intercept.
hold much longer.
Wait a minute, here's my function value. So if I set my
The
x
door won't hold much longer.
plus 2 over x minus 6 equal to 0. This is saying I took my function, I replaced my output with 0. This is saying I want my output to be 0 here. That is where our x-intercepts would come from. Now, why did I say it was going to be easier than this? Well, can you still multiply both sides by x minus 6? Yes. But what is 0 times anything? Well, 0 times anything is 0. So if I multiply both sides by x minus 6, it's going to give me still 0 on the left-hand side and x minus 2 on the right-hand side. Listen, when you have a rational function and you're trying to find your x-intercepts, the way that we appropriately do that, by understanding that when you find x-intercepts, you're setting your function equal to 0, really all you have to do is take your numerator and set it equal to 0. Why? Because firstly, your denominator can't equal 0, and if it does, you get some problems. Your numerator is the only thing that can equal 0, and if you multiply both sides by x minus 6, it'll be 0 anyway. So really just set your numerator equal to 0, and you'll find whatever x-intercepts you have, whatever ones are relevant. So if I subtract 2, x equal to negative 2, what that's saying is that we have an x-intercept at negative 2, 0. Don't just think negative 2. Think about how this is an actual point. So on your graph, you'd be crossing the graph at negative 2, 0, whatever that graph looks like. Last one, the y-intercept. Y-intercepts are always found by plugging in 0, so don't get these two confused. X-intercepts set equal to 0. Usually it's just a numerator for rational functions, and then we solve that. For y-intercepts say, hey, you know what is your, where do you cross the y-axis? Well, that's going to be where your x is 0. So if I take my x value of 0 and plug it in, it says, I want you to find the output when your x value, your input is 0. It's going to give you an output that's on the y-axis. That'd be 0 plus 2 over 0 minus 6, and that's negative 1/3. Again, this thing is a point. You plugged in 0, you got out negative 1/3. That is your y-intercept. I hope that this has made sense and I've illustrated how to find points from graphs. I know it's fairly basic, but sometimes we get confused on this stuff. And I want you to understand it very, very well. Mostly, I need you to understand the domain and the range idea. The domain is a section of the x-axis that your graph is covering. The range is a section of the y-axis that your graph is covering. This is also very important. This last example, make sure you understand that an input value is asking you to find an output value. Giving you an output value is asking you to find an input value, but in both cases, you're really just completing the points. If I give you an input, you plug it in. If I give you an output, you have to set it equal to that output and solve. Find a domain. Well, we know our two issues. We know square roots and denominators, so we know that square roots need to be inside positive or greater than or equal to 0. Denominators need to be
Receiving.
0. So we set the equals here and say message squared that
To
value.
all
Although
servants,
any of
the
those
infected will
Next
decline.
intercept, so
Seekers
on
and
this
wait.
problem, we're just saying your output is now 0 and not 2. So set your output equal to 0. Okay, my f of x is now 0. I'm going to solve y-intercept just 0. So next time we're going to talk about
All service. The infection is in decline. Recover and rebuild.
features of functions that are coming up at us. So I'll see you for that.
All service. The infection is in decline. Recover and rebuild.
Chief, this is the same transmission we received before, but the signal is even weaker. Our walkie-talkies are not powerful enough for long-range communication. We have to build a large antenna. A local library or university would be a good place to search for information on how to make it work.
Let's go there.
Ready for action.
Let's do it. There's nothing left.
On my way. On my way. Infected inside!
Take him down! We need backup! Requesting support!
Sir! Sir! You won't believe what just happened. One of the infected just followed us outside. Into the sun.
We're on the move.
Or
Operator.
what's worse, he seemed to know exactly what he was doing. It took him a moment to give up, but then he returned to the darkness. What the hell is going on?
Better get back there and kill it.
We're running out of resources.
We're not alone here. Operator.
Work's done. Head back to your shelters.
I think I might be done streaming for a bit.